All right, howdy everyone. Good afternoon. Everyone having a good build so far? Final day. Anyone have a chance to see Dave Molnar's talk this morning about security risk detection? Excellent. All right, I'm going to show a slightly different side of this technology. David explained how it could be used. Cannot hear me? Okay. You guys hear me okay now? All right, I'll speak loudly. David talked about how this technology can be used in your development lifecycle, various customer cases, and so on. I wanted to actually focus on the idea of code quality and finding security bugs. So I've got 3 quick slides to go through, and then I'm going to show you demos of actual code that we came up with and that we fuzzed so you can see what this thing does. All right. So security risk assessment is basically the wedding of 2 technologies. One is a set of fuzzers that we have developed inside of Microsoft over the last 10 to 15 years that we have used to eradicate parser bugs in products like Windows and in Office. Am I doing okay? To do that, though, required taking these fuzzers and deploying them to huge rooms full of machines. We had server labs that had 400 to 500 machines in them, and that had all sorts of problems attendant with them. Scheduling the time, you've got a deadline, you need to make sure that your time slot that we could get you fuzzed in time to ship and so on. And so we set out to solve that problem by creating a platform, an automation platform in Azure that allows us to take these same fuzzers but make them pretty much on-demand, click-to-fuzz simplicity of use. And my goal for this session is to show you how this works, show you the bugs that it finds, and hopefully try to get you guys to sign up for a free trial so you can try it out on your own applications. All right, so I'm going to start really quickly here with just a few fuzzing basics. Everyone here know what fuzzing is or have fuzzed before? Anyone not know what fuzzing is? Okay, so there's plenty of documentation on what it is, and I'll point you to it a little bit later in the talk. But for now, fuzzing is automated negative testing. If I have a piece of software that accepts data, it reads a file, it accepts a network packet, especially data from untrusted sources, it can be fuzzed. And the way that that's done is by hammering on that piece of code with intelligently malformed inputs in an attempt to get it to hang, to throw an exception, crash, or so on. And these are the sorts of conditions that hackers can leverage to try to find exploitable bugs in your code. Fuzzing identifies all sorts of bugs I just mentioned. Memory corruption, problems with the indexing, if you're casting improperly, overflows, underflows, all sorts of things. It's excellent in finding logic bugs, state bugs, especially errors in your error handling pathways that aren't usually tested in positive testing. And as I mentioned before, any application that accepts data can be fuzzed. Anything that parses a file, listens to the network, and so on. Native code, managed code, script, anything that accepts data and executes based on that data can be fuzzed. That data can be low level, like a binary format, like a JPEG or an MPEG, or high level, like XML, JSON, and so on. All right, but let's take a look at the code. We have put together a small application called Calendar Reader. What this thing is we set out to build this, and we wanted to make an application that was plausible. Let's write something that anybody who writes software for a living might write themselves. And so Calendar Reader reads in what we call a cal file that contains either an appointment or a meeting request, like you might see in Outlook, for example. It's written in Visual C++ 2017, and it can be built with the free Community Edition. So you can download it and actually test this code out yourself. As I mentioned, it parses the contents of a cal file, which I'll show you what that looks like in a second. We've jazzed it up with a bunch of planted security bugs. And we've tried not to make ones that are super contrived, but they're actually realistic bugs we've seen in code reviews before. These are the sorts of errors that developers make unwittingly. You know, they're not thinking perfectly defensively, and they make a mistake that can be later exploited. Then we took this application and we fuzzed it to see what we could find. Could we find the bugs that we planted in it? And just for matter of reference, we also compiled it with W4 and with prefast, or the /analyze switch, to see which of the issues were found that way as well. So let me show you this. This is available through the new Security Risk Detection Developer Center. I will go ahead and show you what this is. This is available right now. It's at docs.microsoft.com/enus/security risk detection. Oh, you guys don't see that. I'm sorry. All right, I'm going to cancel out of this for right now and show you. Yeah, here it is. Okay, this is the Developer Center. It has a how-to section on actually using security risk detection. It has a set of concepts. It's like a wiki and documentation of what is a first chance exception, what is application verifier, and so on. And then we have this sample code. And the sample code is called Calendar Reader. And you can download this from our public GitHub and actually build all of this and repro what I'm about to show you here. So let me go back here. All right, so here's the question. You guys have all written code in C++, I assume, or at least many of you have. Anybody ever make any sorts of problems like this or errors like this? I'm going to pick one and then have you guys choose the next one. So let's take a double free, for example. We have, all right, so let's see here. I'm going to go to my page on double free. Okay. Here's what's going on in this particular code. You can see okay, so what this code does is it simply reads in the buffer that was read directly from the file. The calendar file format is an element-based, and one of the element types is attachment. It contains a blob of information and the name of the attachment, for example. Standard code problem, so it comes through here, and it tries to get the blob's name from the buffer, and it tries to get the actual content from the buffer, and then it sets the locals to those objects, and then records them so I can later print it out, and then it goes on to the next one to see if there is an additional attachment. In the case where there's an error, say for example, blob name is null, or the blob itself is null, then it goes to an error path, in which case destroys the blob name, destroys the blob, or deallocates, and then deallocates the attachments. And we planted this to the point where the PSE blob name is freed twice. All right, and let me show you an example of what this looks like. So if I come here to a double free, well, in fact, I'll tell you what, I'm going to start with what it should look like. Parses a calendar file, prints out, let me expand this a little bit. Parses a calendar file, prints out all this information. That's expected behavior. Now I have planted a bug in this file that takes advantage of that double free. And if I run it, whoa, I get a crash. How did I do that? Okay, So what I did, and I know this is too much information to actually show you, I encourage you to go download this and take a look at it. This was the sequence of bytes in the cal file that are expected. I purposely modified 2 of the bytes in order to have the blob name be null, therefore triggering the error condition, and we get the double free and the associated read access violation. All right, so that bug is in the code. How do we go about finding it? Okay, I can do a manual code review. That's an option. Compiler warning, nothing's flagged. /analyze, nothing is found. But when we fuzzed it, this bug was flagged by the fuzzer because it was able to realize that manipulating those bytes triggered this fault. And I can go and actually take a look at my fuzzing results here. This is an example of what, if you were looking at the user interface for security risk detection, this is the list of errors that you would get. These have been deduplicated, they have been reproed, they are real bugs. There are no false positives in the list that you get, and each one of them includes the files that we fuzzed that caused the fault. So you can download those and actually repro these issues in your local IDE. And in fact, if I come here, back to here, and show you, this is right here. This is actually a file that was generated by security risk detection, pardon me. And it causes the same problem. So this is an example of a bug that can be found by fuzzing that isn't found by static analysis, isn't found by the compiler. Make sense? All right, anybody want to see another one? Hey, John. Sorry? Okay, this is a particularly fun one. This is a problem that when we were constructing this application, we made this typo. It compiled just fine, and we didn't even know to like create a planted bug file for it to repro it, but the fuzzer found it. Let me show you this thing. All right, so what's going on with this particular bug is at a particular point in the code where we're parsing contacts out of this calendar file, we have len and elen, and we put len instead of elen, and it compiled just fine. But in the error condition, you can see that it's advancing above a buffer by len, but that's not actually manipulating the variable that needs to be manipulated. So it became an endless loop, and the code just hung. Again, fuzzing is very, very good at ferreting out these sorts of like odd cases that you'll never really find through positive testing. This was, see, that's all it took to trigger it, was a modification just by a few numbers down from where it was. All right. This is not found by the compiler. It's not found by static analysis. Admittedly, this is found by security risk detection. We're just not yet reporting these. This is something that we're currently working on and will be in the product soon. We just have to figure out the best way to surface it to the users. And then repairing the buffer is very easy. Just correct the variable that was wrong. Okay. All right. All right, so all of these samples, and I encourage you to download this and see them. We've got, of the 10 planted bugs, we find 8 of them. 2 of them are really not findable by a fuzzer, and the documentation explains why. But in 7 or 6 of the 8 cases, fuzzing found something that static analysis did not. And again, these are not contrived, weird corner case bugs. These are sorts of things that developers make all the time. or the sorts of errors that developers make all the time. So what can you do? Take a look at the documentation. Download the apps, repro these bugs. Each one explains exactly what the problem was, how we caused the bug to happen, how we fixed it, and how it was found by the fuzzer. It's actually very interesting to learn how a fuzzer works and how it manipulates data in order to cause these sorts of crashes. If this seems interesting, if you want to test out and see how this technology can help you find these sorts of buried security bugs in your own code, please sign up for a preview. We'd love to have everybody come and try this on your own code so you can see what it finds. You can do that through Microsoft.com/MSRD. And if you have questions in the future, now I'm here, but in the future, you can always contact us at fuzzing@Microsoft.com. Sound good? All right, thanks everyone. I'll take questions if anybody has it, but our booth is also just right over here at Security Risk Detection on that corner, and I'm happy to walk you through any, software you have, and if you want to know if this is relevant or can be used, I'm happy to help. Thanks very much.